a microcurie point charge is fixed to the origin and a 6 microcurie point charge is fixed to the point on the x-axis where x equals 5 meters, if a 11 microcurie point charge is released from rest at a point on the x-axis where x equals 8, what will be its kinetic energy when it gets a very long distance away from the two fixed charges? Okay. Boom. Boom. So, first thing you do, draw a picture. So we have 9 microcuries fixed to the origin. We have a 6 microcuries fixed to 5 meters. Do 5 meters. Might as well call this one 0 meters. And then we have an 11 microcurie. I think it was at 8. Released from 8 meters. So, what will be the kinetic energy when it gets a very long distance away? Okay, so first thing to notice is these are all the same polarity. They have the same sign on their charges. And so they're going to repel each other. So these two will also repel each other, but they're fixed, so it doesn't really matter. But they're both going to repel this 11, so it's going to shoot off this direction. And you see the phrase, very long distance. That's just shorthand for saying infinity, which you can't really say, so people kind of get around it by saying very large. So there's a couple ways of going about this. The first thing that I always do when I basically approach electrical problems like this, I write out basically the equation for force on a charged particle. So force is Q V cross B plus Q E. And those will be vectors, like so. And so this is the equation for force. And then this is we're looking for how much kinetic energy. So when I think of that, I think of work. And the equation for work equals, do that again. Work equals integral F dot dr. Like so. Yep, and this is usually my starting point in the thought process. So first thing I do is I go to the force equation. So this is V cross B, so it's the cross product of velocity and magnetic field. We don't have any magnetic fields. No, well, we assume that they didn't talk about magnetic fields. There was no magnetic fields mentioned. We're going to assume that it's 0. So this term goes away. Actually, to be more accurate, this term goes away, which causes the whole term to go away. So we're left with force equals Q, which is going to be the charge of our movable particle right here, times electric field. And that'll be the electric field generated by the other two particles. I'm just going to go for one right now, and then we can add them together. So the equation for electric field, E equals K Q1 Q2. Nope. There's only one Q involved in electric field. I'll call it Q2 over, now we can call this one Q1. K Q1 over R squared, where K is Coulomb's constant. It's 8.99 times 10 to the 9th. But since it's 8.99, I'm going to call it 9. It's just simpler and probably close enough, especially for multiple choice. So K Q2 over R squared, okay? And therefore, I'm going to rewrite this as, for any given particle, let's see here. I'm going to look at this one, and then I'll do the next one and just kind of add them. So this would be force, which would be Q1 times E, which would be K Q2 over R squared dr. And if you're a little bit familiar with integrals, you can factor a constant out of the integral. You can pull it out. And if you're not familiar with calculus, that's okay too. I'll show you basically the shortcut at the end. So we have K, which is constant, Q1, which is constant, Q2. I'll do integral, and I'm going to call R 1 over R squared, R to the negative 2. It just makes it easier to use the power rule. K, Q1, Q2. And we're going to be integrating this from, the radius is going to be the distance between, I'm going to say these 2 points here, since these are the two I'm doing first. I'm going to say that this is going to be 3, because it's two of them is 3, and then when this eventually gets off very long distance away, it'll be at infinity. So I'm going to say 3 to infinity. I know you're not supposed to write infinity. That's fine. I don't care. So then to do the power rule here, r to the negative 2 becomes r to the negative 1 over negative 1, evaluated from 3 to infinity. We switch that around, and we get k q1 q2 time, over r, because r to the negative 1 is just 1 over r. And then we'll switch the limits of integration, 3 to infinity. And then we can, maybe I should call that R1. Yes, maybe. I'm going to, nope, I'm good. Okay. Then we can say K, Q1, Q2 over, and then this will be 3 minus K, Q1, Q2 over infinity. Then infinity, whenever you divide by infinity, is going to go to 0. And what we have right here is the energy of a particle due to the position. So to recap what this means is we have two particles here. We have 3, but for now I'm saying that we have 2. We have the 6 microcoulomb and the 11 microcoulomb, and they have a distance between each other of 3. So when we release, there's a lot of potential energy stored there, and when we release it, one of them will shoot away. One of them's fixed. It's okay to say it's fixed. They would have that much energy even if they were both allowed to move freely. So the general equation that I use for work is work equals integral F dot dr. Force, I use this general equation, force equals QV cross B plus QE. And then it kind of simplifies down. And what we get then is this equation here, which you can kind of sort of remember as work equals, let's see, what is it, Q times V? Q times V. So this is voltage, or potential, sometimes referred to as potential, measured in volts, it's a voltage. And you'll often see that for the voltage of a point will be KQ over R. And you can think of that as related to the potential energy here. And then you have this other Q involved. And so the amount of energy due to these two particles next to each other, or in a relative position to each other, is K Q1 Q2 over R. So potential KQ over R multiplied by the other Q. This will be Q1, call that Q2. This is the shorthand formula, and that's kind of the derivation of how you find the energy of a particle. I know I'm giving a lot more background here. If I was just working through this problem, haphazardly to get the answer in a quick and timely manner, I'd probably skip over a lot of this. But it's good to kind of have a background understanding what's going on. That way when something goes wrong, you kind of can feel it. Your spider senses tingle. The way that I remember this formula, like the mnemonic I use, because you'll have a whole bunch of formulas just to know in life. One of the units to measure energy, you have joules, but one of the other ones is electron volts. When you have a very small particles, you'll often use electron volts, if you're dealing with electrons, to measure energy. Well, that's pretty much this formula here, because electron is a charge, and volts is a potential, so electron volts is a measure of work. And so if you remember that electron volts is a measure of work, you can usually use that to kind of mnemonically backtrack what this formula is. Given time, I prefer to work through the formula, the derivation, but it's just a time issue. So you have 30 seconds, work equals QV. You have more time, 20 minutes, 30 minutes, work it through like this. That way you're less likely to make mistakes. Okay, back to the actual question of what's going on here. We plug in more values other than just 3 right there. And we have, so the work due to the 11 and 6 particle will be, 9 times 10 to the 9th, because that's Coulomb's constant, Q1, which is, I guess there's 6 and 11. I can probably remember that. 6 times 10 to the negative 6 times 11 times 10 to the negative 6 all over 3, and I think it's 3 meters, which is pretty good. Pretty good distance, 3 meters, okay? And then we have work due to we still have the 11 and 9. Okay, 11 and 9, remember those? 11 and 9, 9 times 10 to the 9th, 9 times 10 to the negative 6, 11 times 10 to the negative 6, and these are a distance of 8 from each other. Specifically notice that the denominator, number on the bottom, is not squared. Okay, so, what will be kinetic energy? 11, 9, okay. Making sure I get the numbers correct. So then we add these two together, and this will give us our total energy. So this will be 9 times 10 to the 9th times 10 to the negative 12th, because we have 10 to the negative 6 multiplied by each other twice. We also have an 11 in there twice, so we'll factor that out, 11. And we already took care of the negative 6. And then we'll have 6 over 3, this 6, this 3, plus 9 over 8. Okay? Do some canceling. So this will be 10 to the negative 3rd. This will be 2. So we'll have 9 times 11, we'll call that 99, over 1,000, because that's 10 to the negative 3rd, times 2 plus 9 over 8, which is like almost 3. So we get our calculator on clear, 99 divided by 1,000 times quantity, 2 plus 9 over 8, close. So we have 0.309, 0.309, and this is joules. Okay, see what our possible answers are, all the way back over here. So we have 309 millijoules. So that's the same, so we have 0.309 multiplied by 1,000 millijoules per joule. This is joules, cancels, multiply 1,000. We get 309 millijoules. So this will be the answer right there. So to kind of backtrack what happened, we were given 3 particles. They all exert a force on each other. One of them is allowed to be released. We could use the formula of potential energy, work equals QV. Work equals QV. I prefer to derive it when I'm given time. And the derivation has to do with force equals QV cross B plus QE. And that's force. Then work is integral of F dot dr. You plug those in, you work through it, and you get 2 equations for work. Both of the 2 stationary particles will contribute some energy to the unfixed movable particle. And then once it's very far away, i.e. infinity, we'll have some value of kinetic energy. We're not told how fast it's moving, because that'll depend on its mass, but we know how much energy it has total. So hope that helped. Hope that kind of described a way of approaching these problems. Again, if you're stressed for time, work equals QV and go from there. Appreciate it. See you next time.